Hey everyone, it's Ken. In this video, I'm going to show you an example of using the second derivative test in a typical calculus homework problem. So the function that I've chosen is y equals 2x cubed plus x squared minus 4x plus 1. I'm actually going to show you a graph of that right here. And you can graph these yourself. I just go online to desmos.com and type in the equation. And the question that we're going to be asked about this function is, can we find the critical points and then use the second derivative test to determine whether they are local max or local min. And when you look at this graph, you can see the location of a local max and a local min on the graph. Those also happen to be critical points. Critical points are when that first derivative is 0, so when that tangent line is horizontal. You can see it looks like you've got one at x equals -1, and it looks like you've got one between x equals 0 and x equals 1, but maybe we're not exactly sure where that's located. But let's now use mathematics to figure out where are the critical points once and for all, and to find the actual locations of those maxima and minima. So what I'm going to do, so first of all, how do we find critical points? This is a differentiable function, so we don't have to worry about the case when the critical points, maybe the derivative doesn't exist. Here we just need to take the derivative and set it equal to 0. And I'll take that derivative here. I'm going to get 6x squared plus 2x minus 4. The derivative of 1, of course, is equal to 0. If you want to set this equal to 0 and find the values of x that solve the equation, then the best thing to do there is to factor it. And actually, since we know that x equals -1 is going to be a factor from the graph, let's go ahead and try that out. X plus 1. And then you can kind of think, is there another factor that's going to make this work? Well, you're going to have to get something to multiply x to get 6x squared. So you're going to need 6x. And you're going to need something to multiply 1 to get -4, so try just -4. And then that either will be the factorization or this polynomial doesn't factor, but check that out. Mathematics does work out. So that tells me that the two critical points are x equals -1, like we expected, and x equals to 2/3, just because if you plug in 2/3 there, you get 12 over 3 minus 4 equals 0. And we've done now the first part of the problem. We've found those critical points. Let's apply now the second derivative test. And that just says, take the second derivative and plug in those critical points. Is that second derivative positive, negative, or 0? And then we'll make some conclusion based on that. So first, take that second derivative. I'm going to get 12. 2 times 6 times x plus 2. And the derivative of -4 is equal to 0. And so let's plug in x equals -1. So y double prime of -1 will be -12 plus 2 equals -10. So in this case, our second derivative is less than 0. And second derivative test tells me that this is the location of a local maximum. And how can you remember that? Well, remember, second derivative being negative on an interval tells you that you have to be concave down, opening down. So your function is going to look like it's got that maximum. What about y double prime of 2/3? So plug in 2/3. I'm going to get 24 over 3 equals 8 plus 2 is 10. Of course, that's bigger than 0, so that's telling me by the second derivative test, in this case, I'm at a local minimum. So local minimum. And how do you reason that out? Well, similarly to the previous case, your second derivative is positive, so you're concave up, so you're coming up from a local minimum. And so we've answered the problem. We found the location of the critical points at x equals -1, x equals 2/3. X equals -1 corresponds to the local maximum. The problem didn't ask this, but the local maximum is equal to y plug in -1. It's that y value that's the local maximum. I'll let you plug that in and see that. what that value is, and local minimum occurs at the x value, x equals 2/3, and the actual local minimum, again, would be plugging in 2/3 into that original equation, y equals 2x cubed plus x squared minus 4x plus 1. So this is an example of using that second derivative test to take your critical points and see whether it's local max or local min.